commercialization. First of all, it is very important to know that according to first thermodynamic law, energy is not produced nor consumed. It is just here and we convert it from existing to better usable form. It is because energy of isolated system is constant. And according to second thermodynamic law, entropy of isolated systems never decreases. That means that conversion process itself needs some energy and is easier when the quality is reduced. It is when it is a growth of entropy. It is important to know also that the efficiency of conversion increases with increasing potential difference, and even low efficiency can be accepted if the source is available for free and the process, including investment, is economically feasible. According to my opinion, there are two main mistakes in conversion and use of energy. The first mistake is that converter is not used when external conditions are beneficial. You know about non-working wind turbines in windy weather or stagnated thermosolar collectors in sunny days. Main reason is that energy is not instantly required and cannot be stored so simply. Solution is to use various alternative storage systems enabling energy recovery in the same form, but later when needed. And the second very important mistake, according to my opinion, is that low efficient processes are totally ignored. Even low efficiency is beneficial when the source is free and investment costs are feasible. Low potential resources are widely available and their transfer and storage are much cheaper. And that's why I would like to, moreover, very important is to know also that more than 93% of primary energy consumption is now used from fossil fuels. Coal, oil and gas create more than 93% of energy which we use. It is from 2016, and such renewable energies like hydropower create only from this rest, from this 7%, about 1/3, and also nuclear power about 1/4, and such things like solar PV, photovoltaic or wind energy. It is so small amount that it helps us not when we increase it 1,000 times. We need really another concepts, and that's why I would like to show you what can be done in this building industry. We have such a new concept how to reduce the energy demands by aluminum foam heat exchanger. On this slide you can see such a system which is connected of three parts. Aluminum foam thermo-active roofing, which is capable of recovering the heat from solar gains as well as dissipating excessive summer heat surpluses. The second part of this system is aluminum foam heating, cooling, interior sealing heat exchangers, which are impregnated by phase change materials. I explain later why just such a phase change materials. And the second and the third system, part of this system, it is important to know that one of the most common means for storing heat is concrete floor, and the system of the base plate should have a capability, if it is possible, also serving as seasonal storage of summer heat surpluses that can be used for heating of interiors, but also to heating of domestic hot water during winter season. On this slide, you can see such a design of novel house for minimum heating cooling bills. It is connected of two such a very important part, this highly efficient solar energy harvesting using this harvesting can be by using thermo-active aluminum foam based roofing, And it needs to be also the advanced system for repeatable short period storage and release of latent heat from selling aluminum foam heat exchangers impregnated with phase change materials. More detail you can see on this slide. It is this novel house minimizing heating and cooling bills, which is connected of thermo-active aluminum foam roofing, aluminum foam interior heating, cooling, ceiling panels impregnated by PCM, and a system of base plate can have incorporated such a collector to the which allows the seasonal storage of summer heat surpluses. And such a system works there in such a way that during summer nights, the PCM, which is impregnated in the ceiling panels, can slowly solidifies because the heat is removed through the north part of the roofing. During summer days, the roofing is able to heat the water into the domestic hot water tank, and the heat in the interior slowly is removed by these ceiling panels. During winter season, when the sun is shining, it is effectively used for melting of PCM, and this ceiling can store the energy, and it can override the energy which is needed for heating also during these winter days. And on this slide, it is explanation why just this PCM is used for this purpose. You can see performance comparison of PCM with water and rock heat storage systems. It is important to know that PCM absorbs and releases heat at nearly constant temperature, and that's why PCMs are able to store even 10 times more heat per unit volume than usually used sensible storage materials such as water, masonry, concrete, or rock. On this slide, you can see the comparison of thickness of building materials which are required to store the same amount of heat during heating from 20 to 30 degrees Celsius as concrete panel with a thickness of 24 centimeters. If you use brickwork or massive wood, you need slightly larger thickness, about 36 or 38 centimeters. But if you use lightweight construction, which is obviously currently used in building industry, you need more than 2 meters of this thickness of this building construction. But try to imagine that if you use PCM phase change material, only 2 centimeters is sufficient for storing the same amount of heat like 24 centimeters of concrete. But the main disadvantage of this PCM is extremely low thermal conductivity. In this slide, you can see comparison of water, rock, and high density concrete, and with various PCMs. And it is possible to store energy into the water. You see how much you can store into the water. Into the rock, maybe 1/2 of amount which can be stored into the water. In the concrete is the same, only if it is the high density concrete, it is a little bit more, but less than in the water. But in the PCM, you can store significantly large amount, but thermal conductivity is only 0.2 watt per meter and Kelvin. But further development it is PCM based on organic waxes, but it is possible to use also coconut oil and such materials which can be also, which have also melting temperature between 22 and 27 degrees. But very important, it is that all building materials have also thermal conductivity very low, like concrete and such materials. And that's why aluminum foam is for this excellent solution. Here you can see the structure of aluminum foam, which have pores interconnected by small cracks, which always appear during solidification of liquid aluminum foam. It is possible to make also such a homogeneous structure, but for this purpose of heat exchangers, also such a non-homogeneous structure is sufficient, that from one side is more of aluminum in order to have a better thermal conductivity, and from another side is much more of this PCM. Here you can see application of heating cooling aluminum foam sealing panels. We successfully applied to these aluminum foam panels already in 3 applications in Slovakia. The oldest one was already 7 years ago, and it works excellently. It is possible to cool the interior with the water of the temperature 22 degrees and heat with the water 28 degrees, and it significantly reduced the cost for the energy of such a building. On this slide you can see why radiant sealing panels are used for this purpose better, like all systems which are using up to now. There is the large surface transfer of the heat is mostly via radiation. There is fixed installation in the ceiling. There are no constraints in arrangement. It provides coolness or heat directly to the occupants of the room, and only few degrees difference is required for sufficient comfort. And the most important is also that less energy is required to remove or add heat to the space, like you are using conventional air conditioning systems. And from today is very important that air velocity is reduced significantly. That means it is reduced dust movement and also movement of viruses in such spaces. And very important is to use such a system in non-residential building. Try to imagine such your office room, and during overnight thermal storage time, it can start at 2 a.m. Up to 7 a.m. Can be this space chilled by chilling the air into the sealing chamber, and from the exterior it is usable such a cold air, and during this period it can be pre-chilled and all the PCM which is impregnated in the sealing board can be solidified. When working hours start from 7 to 1 p.m., this chilled air supply is bringing only into the interior room, in the interior, and it can circulate and return into the air handling unit in such a way that it will not increase the temperature in the sealing chamber. Only on the end of the working hours during this time of great heat load from 1 to 6 p.m. This air can be circulated also through this sealing chamber, and the rest of the PCM in the sealing board can be can be melted. And that's why it can survive in such a way that then on the end of the night it can be pre-chilled and solidified again using the cold from outside of the building. And it can significantly reduce the cost for this air conditioning. And further, how to improve this energy efficiency is this thermo-active ultralight aluminum foam roofing. On this slide, you can see the basic concept of such a roofing. As you can see, there are the thermal insulation layer above the rafters of pitched roof, which ensuring the waterproofing and creating a barrier to water vapor. And there is the air gap, and under this air gap is the aluminum foam roofing, which is reinforced from one side by basalt granules in such a bitumen ceiling, and from another side, in order to be this roofing very lightweight, it is reinforced by expanded stainless steel sheet. Here you can see the structure of such a roofing, the structure of aluminum foam, which is reinforced from upper side by basalt granules in the bitumen sealant, and from another side it is reinforced by steel, such a mesh or expanded metal sheet. By this technology of preparation of this aluminum foam casting of this roofing tile, it is possible to know that it is possible to do it in such a way that surface layer can be reinforced directly by aluminum, which is melted aluminum is impregnated by the space where these basalt granules are, and matrix is created by aluminum, because this aluminum is impregnated during the forming of this foam. And finally, instead of conclusions, I would like to tell you some important things about innovative potential, how to increase energy efficiency on future buildings. It is important to know that this energy efficiency can be valorized not only how it is used, this building, but this energy efficiency means the amount of energy which is used per unit of product, also such a building construction materials and equipment. It is not sufficient to make energy efficient house where much of concrete is used, because the energy is used during the production of the concrete, and that's why all this can be taken into the account. And if you there are several common approaches how to store the heat. It is possible to store it through sensible heat, in which the heat is simply transferred from a material into the latent heat, in which a phase change occurs, but very large potential have also possibility to store heat by thermochemical reaction. Thermochemical heat, which involves a chemical reaction in order to increase the stored heat energy. And according to this, this energy efficiency of the building can be measured by annual energy use per square meter of floor area, and it can be significantly reduced just by these three ways. Firstly, thermo-active roofing, which is capable of recovering the heat from solar gains, as well as dissipating excessive summer heat surpluses. The ceiling heat exchangers, impregnated by phase change materials are able to maintain sufficient thermal comfort in the interior in an energy efficient way. And according to my opinion, huge potential have also collector working on the principle of thermochemical reaction, which can be incorporated into the air handling systems, and it allows the seasonal storage of low potential heat obtained from summer heat surpluses. According to my opinion, these thermochemical heat storage systems can provide very high energy densities and economic systems with the right choice of materials based on various thermochemical reactions, mainly hydrogenation, but also carbonization, oxidation, and hydrogenation is possible. I think that just this hydration have a huge potential. We are working on this because there are also aluminum foam heat exchangers impregnated with PCM materials which are able to store latent heat of phase transition, can be used also by these systems for thermochemical heat storage.